Hello everyone, this is Sarvesh. In this video we'll be solving question 4 of 6 required for MAT104 Endsem. Okay, so in this question we have to solve y double dash plus 9y equals cosecant of x by the variation of parameters. Okay, so first I will tell how we are going to go through this problem, or more like how the solution of variation of parameters works, and then we'll start solving the problem. So like as you can see, this is the non-homogeneous equation, so we'll solve it basically like how we would for any other problem. So our general solution would contain our homogeneous plus our y particular. So this variation of parameter mainly affects only this y of b. So y homogeneous would be the same like anything else. So like we would assume we would solve this y homogeneous by substituting y double dash plus 9y equals 0. So solving this would give us two fundamental solutions, that would be y1 and y2. So solving, we will be using this to find something known as a Wronskian. Then we would use that to find our y particular. See, generally what we would do is if this y particular would be based on our r of x. So r of x is basically what is given in our right hand side. So like this general form would be a times y double dash, where a is a function of x, plus by dash plus cy equals r of x. Basically a, b and c are all functions of x, and so is r of x. So if r of x is quite simple, like we can use this variation of parameters to solve it. Otherwise, if it is complicated, then this variation of parameters would actually make it a bit harder. So this is useful when this r of x is relatively small and simple. So let's see how to solve this using variation of parameters. So yeah, solving this homogeneous part would give us y1 and y2. So we would use this to find something known as a Wronskian. Wronskian is given by this determinant y1, y2, y1 dash, y2 dash, which is basically y1, y2 dash minus y2, y1 dash. So we'll find this Wronskian. So we'll use this Wronskian to find another value u1 and u2, where u1 would be negative of y2 times r over w dx, and u2 would be just integral of y1 r over w dx. So after finding this u1 and u2, our yp would be u1 y1 plus u2 y2. So we'll find our yp, then we'll just substitute this all the way back over here. So we would find yh already. Here we will find yh as well as y1 and y2. Well, yh would be basically c1 y1 plus c2 y2. So this is much more general. We'll be adding these constants and then adding it up to make it much more general. So this would be our solution for homogeneous equation, and this would be our y particular, and then we would just add both up finally. So this would be how we'll be proceeding with our equation, with our problem. So let's try to solve it. So first we'll have to find y1 and y2. So let's find that one. So that would mean us solving this equation. This is a linear second order differential homogeneous equation. So we know how to solve this. Basically we'll be assuming our y to be taking the form of e to the power rx and then substituting it, and once you substitute it, you would basically end up with r square plus 9 equals 0. The shortcut is just to substitute y to be equal to 1 and y dash to be equal to r, and y double dash to be equal to r square. So basically we'll be using these. It's basically a shortcut. even if you substitute this, what will happen is e of r, e to the power r of x would come outside and then just cancel. So basically ending just substituting y to be equal to 1 and y dash to be equal to r and y double dash to be equal to r square is just a shortcut. So this would mean r square equal to -9. So r would be plus or minus 3i. Well, you can see that the root is imaginary. Well, if a root is of the form lambda plus or minus mu times I, then our general solution would take the form e to the power lambda x into c1 cos mu x plus c2 sin mu x. So now, as we can see from here, this can be written as 0 plus or minus 3 times I. That would mean lambda is equal to 0 and mu equals to 3. So our y homogeneous would be e to the power 0 times x times c1 cos 3x plus c2 sin 3x. So e to the power 0 is 1. So y of h would be c1 cos 3x plus c2 sin 3x. This would be our homogeneous solution. So we know, I just said our general solution for the homogeneous would take the form c1 y1 plus c2 y2, where y1 and y2 are a fundamental solution. So here this would be our y1 and this would be our y2. So now we know y1 is equal to cos 3x and y2 equals sin 3x. Now next we will find our Wronskian, because that's what I already mentioned. We would find our fundamental solution, then we would proceed to find our Wronskian. So our Wronskian would be y1 y2 dash minus y2 y1 dash. Let's find y1 dash and y2 dash. Y1 dash would be minus 3 sin of 3x and y2 dash would be basically dash. By dash I'm meaning the derivative with respect to x. So y2 dash would be 3 times cos of 3x. So we'll use these 4 values and substitute and find the Wronskian. So our Wronskian would be y1 y2 dash. Y1 is cos of 3x, y2 dash is 3 cos 3x minus y2. Y2 is sin of 3x times y1 dash is negative 3 sin of 3x. This would mean 3 cos square 3x plus 3 sin square 3x. Taking 3 common, that would mean we would get cos square 3x plus sin square 3x inside. So we know this would equate to 1. So our Wronskian is just 3. So we have found our Wronskian. Now let's use our Wronskian to find our u1 and u2. So u1 and u2 are given by this formula right here. So let's use that to solve our equation. So u1 would be negative integral of y2 times r over w dx. So we know what our y2 is. Y2 is nothing but sine of 3x. So this would mean negative sine of 3x times r. R is nothing but our right hand side, which is cosecant of x. So cosecant of x over w. W is nothing but 3 dx. So sine of 3x is nothing but 3 sin x minus 4 sin cube x. Okay, so let's use this identity and substitute over here. So our u1 would be minus, would be outside, 3 sin x minus 4 sin cube x times cosecant x. So let me take this 1 by 3 outside as well. So 1 by 3 will come outside. Cosecant x is nothing but 1 over sin x. So divided by sin x times dx. So I can cancel this sin x as well as the power would reduce to 2. So negative 1 over 3. 3 minus 4 sin square x dx. So this would be 1 over 3. Yeah. Okay, so we also, let's use this one more identity. Let's convert this sin square x in terms of cos 2x. So that would help us solve our integral. So we know sin square x is equal to 1 minus cos 2x over 2. So let's substitute that over there. So negative 1 over 3 times our integral 3 minus 4 times 1 minus cos 2x over 2 dx. So negative 1 over 3 times our integral 3 minus 2 times 1 minus cos 2x dx. This would mean integral of 1 minus 2 by 3 1 minus cos 2x dx. So this would basically, we would end up with, okay, so this integral is pretty easy. I mean, you just have to, this would become x, this one would end up becoming x, this one would end up becoming x, and this would end up becoming sine of 2x over x, sorry, sine of 2x over 2. So after doing this and just simplifying it, you would end up with negative of sine of 2x plus x over 3. So we have found our u1. This is just a very basic integral, so there's no point in solving it all over again. It's just that it's just simple. So I just found the solution already. So our u1 would be sine of 2x plus x times negative 1 over 3. So let's now proceed to find u2. u2 is given by y1r over w times dx. So that would mean u2 would be y1, we found y1. y1 would be cos of 3x, would be cos of 3x times r. R is nothing but cosecant x times cosecant x over w, it's nothing but 3 times dx. Okay, so now let's try to solve it. So we also, let's try to simplify cos 3x. So cos 3x is equal to 4 cos cube x minus 4, it would be minus 3 cos x. Okay, let's substitute that over there. And this would be integral of, let me take 1 by 3 outside. This would be 4 cos cube x minus 3 cos x times cosecant x. Our cosecant x would be 1 over sin x. So let me write it as 1 over sin x dx. So now we have to solve this integral. So let's consider sin x to be equal to t. So dt by dx would be cos x. So dt would be cos x dx. So in our integral, let's do this one thing. So this will be 1 over 3 integral of, let me take cos of x common from both. So that would mean 4 cos square x minus 3 times cos x dx by sin x. Now we know cos x dx is equal to dt. So I can substitute this thing with dt. and we know sine of x equals t, so I can substitute this one with equal to t. This would reduce our integral to 1 by 3 times 4 cos square x minus 3 over t dt. Okay, so 4, again cos square x can be written as 1 minus sine square x. Let's further simplify. 4 into 1 minus sine square x minus 3 over t dt. So sine square x is again assumed to be t, so I can substitute that with t. So 1 over 3 integral of 4 into 1 minus t square minus 3 over t, and this would mean our integral would be 4 minus 4t square minus 3 over t dt. This would be 1 by 3 integral of 1 minus 4t square over t dt. After solving this, you would end up with 1 by 3 ln mod of t minus 2t square. Minus 2t square. Yeah. Okay. So here t is nothing but sine x. So I can substitute t with sine x. So our u2 would be 1 by 3 ln mod of sine x minus 2 sine square x. Okay. So now we have found our u1 and u2. Okay. So let's using this u1 and u2, we'll be able to find our y particular. So our y particular would be, so I haven't mentioned it earlier, so let me mention it now. So yp would be u1 y1 plus u2 y2. So we found out u1 and u2 right now, and we already found these two fundamental solutions already, because we used y1 and y2 to find u1 and u2. So if we substitute this, we should, in this equation, we should be able to find our y particular. So y particular would be y1, u1 y1. u1 would be minus sine 2x plus x over 3. This would be minus of sine 2x plus x over 3 times y1. What is y1? y1 would be cos of 3x. y1 would be cos of 3x plus u2. u2 is nothing but this. u2 would be 1 by 3 ln mod of sin x minus 2 sine square x. Sorry, this would be minus 2 sine square x times y2. y2 would be sine 3x. So this would be our yp. So now we have found our y particular and y homogeneous. Homogeneous is nothing but, we have found it out earlier. So y homogeneous is over here. So let's add both of them up. So our general solution, y would be given by c1 times, what was our y homogeneous? c1 cos 3x plus c2 sin 3x. So it would be c1 cos 3x plus c2 sin 3x plus, so this would be our y homogeneous plus our y particular. Our y particular is right over here. So that would be plus cos 3x times negative 1 over 3 times sine 2x plus x plus sine 3x times 1 over 3 times ln mod of sin x minus 2 sine square x. So this right over here is equal to our y particular. So this would be our solution for our linear ODE.